Hello there. I'm Alan, of course. Most of you already know me, but I see some new faces here, which is awesome. The purpose of this talk is not just to remind you that Nigel was not the first person to walk around in these corridors with a Hawaiian shirt, but it's also to tell you guys a little bit about the research projects that I've been focusing on after graduating from COSIC, or after leaving COSIC rather. So this is joint work with Benedict Buns and Ben Fish, Stanford rock stars. And the title is actually really misleading, unless you are familiar with the setting. So what we have is Trustless-Setup SNARKs. Who here is familiar with what a SNARK is? Okay, that's roughly half of you. That's good. So for the other half, SNARK is a very succinct zero-knowledge proof, which is something that you need in the context of privacy-preserving cryptocurrencies, for instance, where you make a transaction and you hide the amount, but you prove in zero knowledge that you're not introducing new money into the ecosystem. You prove in zero knowledge that the inputs, sum of inputs and the sum of outputs are equal in your transaction, and you're also hiding the origin of the money. So using SNARKs, you can very efficiently audit the correctness of the financial system, but you still get to preserve privacy. And if we look at the landscape of zero knowledge proofs that can accomplish such a task, there's a bifurcation between proof systems with succinct verification. That's where the verifier is really fast, which is good because in cryptocurrencies, your network consists of nodes who constantly verify every transaction on the network, and if your verification is fast, that's good for the nodes because they don't have a lot of work. The problem, though, is that most of the time they have a trusted setup, so they fall outside of the green circle. That means that in order to instantiate the cryptocurrency, there has to be a trusted setup party between trusted people who have to forget their randomness. And if they remember the randomness involved in this trusted setup, well, then they can forge transactions that are actually invalid, but they will look valid to the network validators. So we don't like trusted setups because we don't like to trust people. On the other hand, if you go for trustless setups, well, it looks like you have to sacrifice succinct verification. There are solutions for zero-knowledge proofs for general-purpose computations whereby you don't have to trust anyone at the start. But generally speaking, they take a lot more work to verify, or it takes a lot more work to verify those proofs. In the intersection, we have a couple of works. So this builds on the PCP theorem, and it puts the PCP theorem into a Merkle tree, and that lets the verifier query the Merkle tree. And it is technically speaking in this intersection because it provides succinct verification and trustless setup. The problem is that in order to create this PCP, this probabilistically checkable proof, the prover has an insane complexity. So these things are not really practical because the prover cannot prove more than really simple relations. And well, at crypto earlier this year, some people noticed that you can replace the Merkle tree using vector commitments based on groups of unknown order, and that improves the verification part. It turns the proofs into constant size, which is cool, and it makes verification faster, but it doesn't do anything for the prover. And that's why the Stark crypto system is really so remarkable, because they both have succinct verification and trustless setup and a scalable prover. So the Stark cryptosystem is really quite remarkable, and this is also the context for this work, DARK, Diophantine Arguments of Knowledge, and I'll get into exactly what that stands for and what that means. So Darks and Starks are very comparable, and rather, I guess I shouldn't say Darks because it's really a family of techniques, but still, when compared to Starks, they both have succinct verification and trustless setups, which is really cool. But then in terms of the information theoretical compiler, how you go from the algebraic representation of your computation into something that you can prove, that's where Stark uses a particular compiler, and our techniques work with any compiler you like. On the other hand, when you look at the bottom layer of this compilation process, the cryptographic primitive involved in Starks, that's a hash function, whereas we use groups of unknown order. This is, it has much more structure algebraically, and therefore it allows us to reduce the work of the verifier and shrink the size of the proofs. From groups of unknown order, we build a polynomial commitment scheme, whereas Stark builds the fast Reed-Solomon IOP of proximity from hash functions. And a polynomial commitment scheme and a Frye protocol, they are very interchangeable. What a Frye protocol does is it says, here is a commitment to a polynomial, and it allows you to prove that this polynomial is not of very high degree. In a polynomial commitment scheme, what you do is you say, here's a commitment to a polynomial, and you get to evaluate this polynomial in particular points. So it is a commitment scheme for polynomials, but in addition to the classic commit and open functions, you have a protocol called eval, which you instantiate with point z and an evaluation y, and it proves that when you evaluate the polynomial that is committed to in C, the output is y. And the point of this protocol is that the verifier should be able to verify this proof and this relation in particular with much less work than looking through all the coefficients of f. So in the end, you don't even need to transmit the coefficients of f, you can just transmit the commitment C. We want the commitment scheme to be binding, and we want the evaluation protocol to be an argument of knowledge. This means that the prover establishes not just that this relation is true for some f, but also that there is exactly one f that he knows for which this relation holds. All right. So in a diagram, you would have the prover providing the commitment to the polynomial to the verifier. The verifier would query a point, possibly at random, and the prover would provide the verifier with the value of the polynomial at that point, along with the proof. And the question is, what does this proof look like? And I wrote it here as though it's a message on this line, but it's actually an interactive thing. So what does the proof look like? Here I'll show it to you. And I'm going to use a commitment scheme, or rather I'm going to make abstraction of the exact commitment scheme, and I'll instantiate this commitment scheme later on. But I'm going to need particular properties from this commitment scheme, namely linear homomorphism and monomial homomorphisms. So at the start, we have the prover who possesses the full polynomial, and we have the verifier who possesses only a commitment to the polynomial, and both possess the evaluation point z and the value of the polynomial y. So what the prover is going to do is he's going to split his polynomial into the left part and the right part, and These might be called FL and FR of x. And both of these polynomials have half the degree, roughly speaking. And he's going to send commitments to these polynomials to the verifier along with their evaluations in Z. And at this point, the verifier needs to know that these commitments really represent the splitting of this commitment. So that's where this monomial homomorphism comes into play. He needs to be able to shift the commitment to the right part by the necessary number of digits. And then if he can do that and homomorphically add commitments, then he can check against the commitment he already received that F and FL and FR check out. If they do check out, he sends a random weight to the verifier, and the verifier gets to combine the two halves by randomizing the left half. He also has to combine the two evaluation points using the same weight, and also the verifier has to combine the two commitments using the same weight once again. Now if you look carefully at the blue text in the top line and the green text in the bottom line, you will notice that they are of the same form. And the only difference is that the degree of the polynomial f here is twice as large as the degree of the polynomial f prime here. So we went from a statement of degree d to the same statement but of a polynomial of degree d over 2. So we recurse, and if you do this often enough, eventually you will get a polynomial of degree 0, which you then just send over in clear text and allow the verifier to verify the remaining relations. So this is the essence. Of course, the big question is, how do we instantiate this commitment scheme? Because we need to be able to commit to polynomials of arbitrarily high degree, and that's an infinite space, and yet we want our commitments to be finite in size. And we need to have linear relations, or we need to enable the verifier to compute linear relations, and even monomial relations. So finding a suitable commitment scheme, that's a challenging task. How do we do that? That's where we use groups of unknown order. We know 3 groups of unknown order, and you might even say that the UFO group, that's just the RSA group. Anyhow, in the RSA group, you work in the integers modulo the product of 2 large primes, and this product cannot have a known factorization. So you cannot generate n and still hold on to P and Q. Which means that this group inherently has a trusted setup. Because whenever you want to generate n, you have, or whenever you want to have someone generate n, you have to trust that they actually forgot the prime factors P and Q. An alternative to the RSA group is the UFO group, where UFO stands for unfactorizable object. And instead of sampling n as the product of 2 large random primes, you sample n as just a large random number. And with high probability, it will contain 2 large enough primes such that factorizing this n is hard. The problem is, of course, that n has to be huge, and as a result, your group elements will be huge. But the nice thing is that there's no trusted setup. Now, if you want the best of both worlds, the group elements roughly on the order of size, roughly on the order of RSA group elements, and no trusted setup, that's where you can use the class group. In order to sample a class group, what you do is you sample a prime that is equal to 3 modulo 4, or maybe it's 1, I'm not sure about that issue, and that defines your class group. There are sub-exponential attacks, so representing group elements is takes roughly the same space as it does to represent RSA group elements, but the nice thing is that there is no trusted setup. So we're going to focus on class groups, but in principle we can make complete abstraction of which group we use, and just note that since there is an instantiation of groups of unknown order without trusted setup, our protocol works without trusted setup. All right, none of these groups of unknown order are post-quantum, and that's probably necessary because Shor's algorithm, exactly what it does is find the order of an element. So it would be interesting to find a candidate that can salvage the techniques involved in this work and still provide quantum security, but I don't think it can be a group. All right. We rely on two hardness assumptions. One is the age-old strong RSA assumption, which state that it is hard to compute arbitrary roots of given group elements. And the other assumption is the adaptive root assumption, which, despite being far newer, is the complete dual of the strong RSA assumption. It states that it is hard to compute given roots of arbitrary group elements. From these two assumptions, you can derive other assumptions, including it is difficult to find any element of known order. And that's exactly what allows you to compress in your commitment element of arbitrary size into an element of short size, because you don't know the order of the integers, you don't know where to chop them up into pieces. So the only way you can get a sound commitment is by committing to the entire integer. And the nice thing is that these assumptions are falsifiable. Oftentimes, SNARKs are built out of assumptions that cannot be falsified. And if you ask me, that's a bad thing, and our falsifiability is a good thing, but other people may differ. So what can we do with groups of unknown order? I'd like to show you that groups of unknown order are really, really powerful, and they derive their power because they apply to Diophantine relations. And this is, by the way, where DARK stands for. Diophantine Arguments of Knowledge allow you to prove Diophantine relations, which are polynomials with integer coefficients and integer variables. And you can show that they evaluate to 0 or that you know a solution. So for instance, Fermat's last theorem is a Diophantine equation, and so is Pell's equation, but as soon as you have an algebraic number or a transcendental number, then it's no longer a Diophantine equation. But if you really like trigonometric identities, there is always a way to turn it into Diophantine once again. An argument of knowledge refers to the fact that you can prove that you know a solution without having to reveal it, or, well, I guess without revealing it part makes it into zero knowledge, but the proof of knowledge states that you know the solution. And relations of this, where x and y are vectors of integers, and p has integers coefficients, they are really, really quite powerful. And to illustrate that they are quite powerful, I will show you how to do a range proof in constant size. Range proofs is what you need to do when you make a private cryptocurrency transaction, and you need to show that your new balance is still positive, because if you're allowed to make your balance negative, why wouldn't you? You get to keep spending. So you want to show that your new balance is positive, but you want to hide the amount of the transaction. There are existing solutions for this. For instance, Monero uses bulletproofs, and Zcash uses SNARKs, but they are really very, very complicated, and if we're trying to solve that one task, groups of unknown order, and in fact Diophantine arguments, give you a very, very nice way to do that. So we have an integer x that the prover knows, and the verifier only knows a commitment to x in the form of a random group element, known group element, raised to x. And both verifier and prover know the lower and upper bound. And what we're going to do is we're going to use some Diophantine complexity argument to find three integers, a, b, and c, such that the sum of squares of a and b and c equals 4 times u minus x times x minus l plus 1. It's easy to see that the right-hand side is positive because they are integers, which means that the left-hand side has to be positive, which means that u minus x and x minus l both have to be positive, which means that x lies in between l and u. And you might wonder, where do 4 and 1 come from? Well, that's just an artifact of the algorithm that allows you to find a, b, and c efficiently. All right. So the prover has found 3 such integers, and now he's going to commit to them, and that's basically the entire proof, because the rest is hidden behind homomorphic operations that the verifier should be able to perform, and that allows the verifier to verify this relation in the exponent of g. And you might say, yeah, well, you really hid those homomorphic operations. Yeah, okay, but you send a couple of more messages back and forth, and then you can establish that g to the x squared really is g to the power x squared, and so on. But the point is, you only have a small finite number of terms for which you have to show these homomorphic relations, which means that your proof is constant size. The proof for Zcash transactions is also constant size, but they require a trusted setup. The proof for bulletproofs is not constant size. It actually grows with the size of your range. We don't know how to do constant size range proofs without trusted setup in any other way but using groups of unknown order. That does solve only a part of the problem, though, because we have a very powerful proof system for integers, but what we really want to show is arguments holding for polynomials over a finite field. So it's not quite the same thing. And that means that we have to find a way to encode polynomials as integers, because that's the input of our argument system. So what we're going to do is we're going to pick a q, which incidentally has to be odd, and q is much larger than p. And what we're going to do is we're going to interpret the polynomial f as a polynomial consisting of integer coefficients, and we're going to evaluate f in q. And that's our integer encoding. That's it. Because q is so much larger than p, this is injective, given a set of canonical representatives for zp. And this is also homomorphic, assuming that q is large enough. You get to combine linear relations, and you even get to multiply encodings of polynomials, and then you get the encoding of the product, assuming q is large enough. And that's actually also where our monomial relation is going to come from. Q to the j as a constant factor actually represent x to the j after encoding, or before encoding, depending on your perspective. So this allows you to do monomial relations too. That's nice. But you have to make sure that there's no overflow in your QRE expansion. because once overflow occurs, then all bets are off. Which means in practice that Q has to be large enough. So getting back to this slide, we're in a position to answer the questions raised here. How do we commit to polynomials? Well, we just raise a random group element, random but known group element, to the encoding of the polynomial. That's it. The encoding is an integer, so we can raise the group element to the integer. The linear relations come for free because you can multiply group elements and you can raise them to scalar powers. That's not an issue. The monomial relations, well, that's actually still an issue, because on the previous slide we saw that we can multiply, or rather raise, a group element to the power q to the power j, and that shifts the polynomial by the desired number of digits, so we can raise the commitment to the right half polynomial to the power q to the d prime plus 1, which shifts it by the necessary number of digits. But this is kind of expensive, because q is already a large number and we're going to raise it to a large power. And we don't know how to chop q to the d prime into pieces because we don't know the order. So what we're going to do is, instead of allowing the verifier to compute the entire thing from g to the fr, we're going to send both g to the fr, evaluated in q, and the result raised to the power q to the d prime plus 1. So we're giving the verifier two things, and that allows him to check this equation, and he still has to verify that CR star really is CR raised to the appropriate power. And you might say, how does he verify this? If this step was expensive, then this step has to be as expensive surely too, right? So how do we solve that? Well, actually, we have a protocol for exactly this task. This is Veselovsky's proof of correct exponentiation in groups of unknown order, for which he won the Best Student Paper Award at Eurocrypt earlier this year. And I don't have to go through the exact construction of the proof, but it turns out that this huge exponent that the verifier has to deal with has been turned into two very small exponents. And of course the verifier has to send some random bits, but we can turn this non-interactive with the Fiat-Shamir heuristic, and that's perfect. That's perfect for our situation. So that completes the picture, because now we have an evaluation protocol and we have a commitment scheme. So we have a polynomial commitment scheme. So the question now is, what can we build with it? And the abstract notion of what you can build with polynomial commitment schemes, we seem to gravitate towards polynomial IOPs. So an IOP is an interactive oracle proof of knowledge. So in the PCP, the prover sends a very large proof string to the verifier, and the verifier checks a few random positions. In an IOP, this interaction happens a couple of times. And in a polynomial IOP, the prover will send commitments to polynomials, and the verifier can evaluate this polynomial, these commitments to polynomials, in points of his choosing. So where does this fit in the compilation process for proofs of correct computation of arbitrary computations? So generally we start from some computational claim, which we then turn into an arithmetic representation, typically using finite field elements, maybe also polynomials. And then we're going to turn this arithmetic representation into a proof system with statistical soundness using some information theoretical compiler. And then we're going to turn this proof system with statistical soundness into a proof system with computational soundness using some kind of cryptographic tool. And that's exactly where dark tools fit. We fit at the bottom rung of this ladder. We provide an alternative to Merkle trees and to pairings to do polynomial commitments. But it's worthwhile thinking in the layer above, what can we do there with polynomial IOPs? Well, we can obviously do SNARKs, because all you need there is a polynomial commitment scheme. And we also noticed that there is a generic construction for point IOPs, which is where you query specific coefficients of the polynomial that's committed. And once you have these two primitives, then you get sonic, which is a very popular SNARK with trusted setup, because it has an efficient prover. And since we can drop the trusted setup, we get supersonic. But this picture is not complete, of course, because really the most general type of IOP there is the linear IOP, where the verifier provides a huge vector and gets back the inner product of this vector with the committed proof. And the linear IOP actually captures essentially every general purpose zero knowledge proof system there is. So it would be cool if we could realize linear IOPs from polynomial commitments, but that doesn't seem to be very feasible. But if we look closely at these various proof systems, well, we can actually capture them as special cases of something weaker, something called an algebraic linear IOP, where the verifier doesn't specify the entire vector, but only an input to an arithmetic circuit that is then expanded, providing the entire vector for the inner product. And we can do this too if we have multivariate polynomial commitments, which we do in the dark framework. So we can actually achieve essentially any general purpose zero knowledge proof system out there, and we can drop the trusted setups, and we can drop the sometimes linear verification times in favor for logarithmic verification times. So looking at this picture again, it's accurate, but what's missing is a diagram showing that we can actually bring all these proof systems into the dark family. Thank you.